So say Jason solved the following system and got the solutions x equals -1 and y equals 2, x equals 0 and y equals 3 for this system of equations. Is this solution correct? If not, why not? Okay, so how can we test this? Well, one way we could do this is we can graph. Okay, if we have to do this analytically though, we can just substitute in. And what's the criteria then if we substitute in these points? Okay, so if I substitute in x equals -1, so 2 times -1 squared, and y equals 2 equals 0. Okay, I get 0 equals 0. That's perfectly good. Okay, so x equals 1, y equals 2 it fits into this equation. Now, does this mean it's a solution for this system? Well, no, because remember, if you think of what this graph looks like, this is basically a parabola. And what all this confirms is that x equals -1, y equals 2 is actually some graph on that parabola. Okay, in fact, it just means it's there. So I have to test that same coordinate into this system. Okay, so I have to plug that in. X equals -1, y equals 2. Okay, so I get 1 minus 2. So it's going to be 1 minus 2 minus 2, so I get -3 equals 5. Okay, that coordinate does not fit into this parabola. Okay, so if I were to graph this, the graph of this, if I'm not mistaken, I think it's going to look something like, some graph that looks like this. Okay, and what it means is that red dot there is not a coordinate on the blue dot, so that can't be it can't be the solution, because remember, the solution occurs at the intersection point. So this is not a solution to this equation, right? So x equals 1, y equals 2, sorry, -1 and +2 is not a solution. Now we could always test this again, the other coordinate, into the same system. X equals 0, y equals 3. So I plug in x equals 0, 2 times 0 squared minus 3 equals 0. Okay, well, -3 is not equal to 0, so we know that this coordinate does not exist on the first graph, so it cannot be a solution to both of them, because it has to intersect. It has to be a coordinate on both graphs. Okay, just to double check here, we can check to see this is, in fact, doesn't fit into here. So if we plug it into here, we get x equals 0, so we get 0 squared plus 2 times 0 minus 3 equals 5. Okay, again, -3 does not equal to 5. That does not fit into that system. Okay, so we have this second coordinate here, x equals 0, y equals 3, is not even a point on either graph. It's just some random coordinate on the xy plane. So one way we can test systems is we can just plug in, just like we can do with a regular equation, we can just plug into x and y and see if they fit, but they have to fit into both equations for it to be a solution to the system of equations. Okay, so we want to know what these system solutions look like. So if we want to represent a solution to the following systems, okay, and we can write a potential system with this. Okay, so linear quadratic system would look like this. So if we have some quadratic, some line, and it's potentially going to have two solutions. Now, a linear quadratic solution can have one solution, and the way that happens is we can have well, the easiest way is to make this into a horizontal line where it just touches a vertex. Although it is possible that we could have a tangent line as well, where it just touches there. Okay, now I'm going to set this up as a horizontal line, because this line where it intersects this parabola is going to be easy to determine, because where the parabola's vertex is where the horizontal line will occur. So there's my linear quadratic system with one solution, and I'll write an equation for this. So y equals, let's just say, x squared minus 2. Okay, that's one equation. The second equation would be just y equals negative 2, and this will have a solution, just one solution where it's tangent. If I go ahead and solve this, we can see that at negative 2 equals x squared minus 2. Okay, x squared equals 0, x equals 0, and then plugging it back in, y equals negative 2. That represents the solution to this system, and that is that coordinate that we have a tangent at the vertex. So a quadratic system with two solutions might be something that looks like this. Okay, so I have a parabola here, and an easy way to make this have two solutions is we just have upside down parabola, and then we have two solutions. Okay, so if I want to come up with an equation for this, I can just write an equation for the quadratic. So I'm just going to have a quadratic that goes up, and I'll write the equation for the quadratic that goes down. So I'm going to write negative x squared plus 2. Okay, so there's upside down quadratic, a right side up quadratic. This is going to have two solutions. Okay, when I solve this, I end up with negative x squared plus 2x equals x squared minus 2. So 2x squared is equal to positive 4. X squared is equal to 2. X equals plus minus square root 2. Okay, so those solutions will be plus and minus square root 2. And then if I remember, I need to solve for y, so plugging in plus minus square root 2, I'm going to end up with looks like 0. So this is, I'll just draw this a little bit more accurately because it's a parabola that's facing up with a vertex at negative 2. Then I have one that's upside down with a vertex at positive 2. And when x equals root 2, y equals 0. Okay, so y equals negative of root 2 squared plus 2. That equals to 0. So y equals negative of negative root 2 squared. Y equals 0. So my two solutions are root 2, 0, and negative root 2, 0. Those are my two solutions for this system. And you can see that they would intersect at those points there.